Now we're thinking about magnetism, which is like electricity in many ways. You see the same pattern in magnetism as you saw in electricity. In electrical phenomena, you've got a source, which is some kind of a charge, and in the space around that charge, there's an electric field produced by this charge. There's electric field in that space because there's a charge there. And then when a second thing, which is another charged object, comes into that region of space and then feels the electric field, because it feels the electric field, there's now a force acting on it. So the force on the second particle to come into that area, when that particle lands at a particular point, it feels a force which is just equal to charge of the second thing times the electric field at that point where the charge has landed. Same thing happens in magnetic phenomena, but the source is different. In magnetic phenomena, the source isn't just charge, it is moving charge, either a current or could be just one charge with a non-zero velocity. Just some one moving charge can create a magnetic field, or obviously magnets create magnetic fields, but as we'll see, the magnetic field produced by a magnet is really, when you look at things on the atomic level, the magnet's magnetic field is really due to charges that are moving, specifically electrons moving around inside an atom. But anyway, the moving charges, they are the source of a magnetic field, so you get a magnetic field in the space around any moving charge, and then a second thing comes into that area, and the second thing is just like the first thing, either a current or one charged particle with a non-zero velocity, or a second magnet. And when this second thing feels the field that was produced by the first thing, just like in the electrical case, the second thing feels a force, a magnetic force. I won't write down the rule for magnetic force. We'll do that next time. It's kind of a complicated rule. Right now, we're just thinking about what kinds of field are produced by different kinds of sources. And we'll keep things relatively simple by thinking about only one source, current in a long, straight wire. So let's say we've got some current in a wire, and the wire is perpendicular to the plane of the blackboard, so that the current is pointing this way, pointing straight at us. We have a special symbol for that kind of thing. Looks like that. The bullseye target kind of symbol just means something with a direction, and the direction is perpendicular to the plane of the blackboard or perpendicular to the plane of your paper and pointing at us, as if you were just looking at the tip of the arrow. So current pointing that way, current creates magnetic field. What is the magnetic field like? We can draw magnetic field lines. Just as we could draw electric field lines, we can draw magnetic field lines, and what those magnetic field lines look like is is really determined by a fairly simple rule. Two rules, really. Anytime the wire is straight and long, and you're away from the ends of the wire, the magnetic field lines make concentric circles about the wire, and the circles lie in planes that are perpendicular to the current. So we could draw those circles in this plane. And notice I've tried to make the spacing bigger as the circles get larger. That's because we interpret magnetic field lines exactly the same way we interpret electric field lines. When the field lines are spaced closer together, that means stronger field. When the lines are spaced farther apart, that means weaker field. And just like in the case of electric fields, when you're close to the source, the field is stronger, and when you're far away from the source, the field is weaker. But, of course, these field lines, these magnetic field lines, have a flow to them, a direction, just like electric field lines did. So in this case, the field lines are going to flow either clockwise or counterclockwise, which way, and the way is determined by a so-called right-hand rule. Take your right hand, point your thumb in the direction of the current, which is this way in this case, and then curl your fingers into a circle, and the direction in which your fingers curl tells you the flow of the circular field lines. So my fingers are flowing this way, counterclockwise. So that means the circulation of the field lines is counterclockwise. And then from that, we could figure out exactly what the magnetic field is like at any particular point. And we do that by interpreting the magnetic field lines just the same way that we interpret the electric field lines. They're curved, so we look at a straight line that's tangent to the curve at the point we're interested in. Let's say we want to find the magnetic field right there. Well, the circle, the straight line that's tangent to the circle at that point is just a vertical line. The field will point one way or the other, up or down, along that vertical line, just the same as we had for electric field. If the field line is curved, draw a straight line that's tangent to the curve, and then the field points one way or the other along that line. And which way, up or down, is indicated by the way the field lines are flowing. So field lines are flowing this way. So this is the direction of the field at this point caused by this current. And this point is close to the source, so it's going to have a stronger field. I'll indicate that with a longer arrow. Similarly, in the same horizontal plane, if you look at this point or you look at this point, again, the straight lines that are tangent to those circles will be vertical lines, and so the field at those points will point either up or down, but the flow of the field lines tells you that the field at those points points up. These points are farther away, so they have weaker field than at this point, so I'll indicate those with shorter arrows. Right. Decreasing field strength as you get farther away from the source. And then say the same thing would happen if you look at points like that in the in the same vertical plane that has the current in it. Straight tangent line is horizontal, so the field here, right at the bottom of this circle, would point either straight to the left or straight to the right horizontally, and because of the counterclockwise flow, it points to the right. And likewise here, and likewise here. And then up above, but in the same vertical plane, let's try to make that up better. In the same vertical plane, you're at the top of the circle, so tangent lines, straight tangent lines that are tangent to the circle at the top of the circle are again going to be horizontal. So again, at this point, the field will point one way or the other along that straight tangent line. There's the tangent line, and so the field will point either left or right, and because of the flow of the field lines, the field is left. And same here, leftward field and leftward field, but getting weaker as you get farther away. So that's what field lines would look like if you had a current pointing straight at you. If you turn the direction of the current around, so the wire is still perpendicular to the plane of the blackboard, but now the current is going into the blackboard, going away from you. We'll still get concentric circles, but because we've turned the direction of the current around, that also turns around the direction of the field. And we can see that by, again, using the right-hand rule. First, here's our symbol for something with a direction where that direction is perpendicular to the plane of the blackboard or the plane of the paper. You could sort of think of this as you're looking at the back end of an arrow as the arrow moves that way. Just sort of the feathers at the back end of the arrow are symbolized by that X. So, again, concentric circles for all centered on the current. That's what the field lines look like. But now they have to flow in the opposite direction because you turned around the direction of the current. Just the way if you have a charge and you change the charge from positive to negative, the direction of the electric field lines will flip. And so the direction of the field lines here flip. And let's see how that works. Just use the right-hand rule again. Thumb always in the direction of the current, which is going into the blackboard, away from you this time, and curl your fingers into a circle, and then those circular fingers will show you the flow of the field lines, which in this case is clockwise. So, in other words, if we wanted, again, to find the field strength at this point, look at the straight line that's tangent to the curve. The field points one way or the other along that straight tangent line, up or down because the tangent line is vertical, but the flow of the field lines clockwise tells you which way it has to be down in this case. Or let's look at a point here, not in the same horizontal plane as the current, but up at a 45-degree angle. So look at this point and do the same thing. Draw the straight line that's tangent to the curve at that point. the field must point one way or the other along that curved line, along that straight tangent line, sorry. So it's point either up to the left or down to the right, but the flow of the field lines tells you that it has to be down to the right. Now, there's another way of thinking about this, all these circles and this right-hand rule, which for some people it's a little easier to think about. I call it the radius tangent method. So let's say here's a source of magnetic field, a current flowing this way. It's the point, this is the symbol for something that has a direction pointing out of the paper, pointing at you. And so what do we know? We know that all the field lines are circles perpendicular to the direction of the current, circles in the plane of the blackboard, for example, in other words, and they're going to flow counterclockwise. Let's imagine a point right there. What's the direction of the field there? Well, imagine the magnetic field line that passes through that point. Right, the magnetic field line that passes through that point is a circle. And the field at this point points one way or the other along a line that's tangent to the circle. Now imagine drawing a line that takes you from the source to the point that you're interested in. That. Let me, all right. Let me redraw this a little bit here. Okay, it's just a basic fact about the geometry of circles that radii and tangent lines are always perpendicular. So in other words, if you got a source and a point that you're interested in, just draw the line that connects the source to the point that you're interested in. That is going to be a radius of the circular field line that this point is on. And being a radius, the tangent line to the circle is perpendicular. So you just draw this line and then draw the line that's perpendicular to that, and you have the tangent line. The tangent line along which the field must point. And then go back to the right-hand rule to see whether the field actually points up to the left or down to the right. And in this case, thumb in direction of the current, curl your fingers into a circle, and your fingers will circulate counterclockwise, so the field lines flow counterclockwise like this. So at this point, the field has to point up to the left. Let's look at another example of that in a case where we have two currents, two sources, which means we have two magnetic fields. So the actual magnetic field at any point is a net field, a sum of the field caused by one current plus the field caused by the other current. Okay, so let's say our currents are like this. We'll call them current A and current B. And then here's a point that we'll call X. And to keep things simple, we'll say that the distance between current A and X is the same as the distance between current B and X. And also, to keep things simple, we'll say that the magnitude of this current is just the same as the magnitude of this current. By having two equal currents and two equal distances, that will mean that the field here caused by A has the same strength, same magnitude, as the field caused by B. The strength of a magnetic field depends if the field comes from a long straight wire, or if it comes from a long straight current in a wire. The field depends on only two things: the strength of the source, in other words, the strength of the current, and distance away from that source. So the field here is a net field, sum of the field caused by A plus the field caused by B. Okay, first let's think about the field caused by A at point X and do it in the radius tangent way. Just draw a line from the source to the point that you're interested in, and then draw the line that's perpendicular to that. And this has to be a radius of the circle that this point lies on, the circular field line that this point lies on. And then the tangent line to the circle at that point is going to be perpendicular to the radius that points to that point. So the field points either up to the right or down to the left, and right-hand rule will tell us which way. This shows that the current is flowing away from us, so thumb goes this way. Thumb points into the blackboard, curl your fingers into a circle, and that shows how the field lines circulating clockwise. So the field at point X from A is down and to the left. And I'll just call it I'll just use dash lines for that so I can differentiate between the field caused by one particular current and the net field. So this is the magnetic field caused by A. Right? B is our symbol for magnetic field. M is a symbol that's already taken, right? Used for mass. So there's the direction of the field here caused by current A. What about the field here caused by current B? Same thing. Draw a line that connects the source to the point. Then draw the straight line that's tangent to that line. Like that. And there you have the line along which the field caused by current B must lie. The field caused by current B at this point is going to point either up to the left or down to the right, and the right-hand rule tells us which way. Thumb in direction of the current. This is the symbol for something pointing out of the blackboard, pointing at you. So curl your fingers into a circle and your fingers curl clockwise. So the flow of all the circular field lines that correspond to the field caused by current B are clockwise. So that means that at this point, the flow is like this. So the field will point up this way, up to the left. That's the field caused by current B. And now the net field, what is that like? This takes us way back to something that we did in just a very little bit in 2201. You can show how two vector things add together to give you the net result by so-called tail-to-tip picture. Here's the field caused by A, and then you connect to this arrow, the arrow that represents the other thing you're adding in, the field caused by B. And the two things that are added are always connected tail to tip. It's another one of those things that's really easy to say and makes perfect sense when you listen to it, but it still takes work to get used to it. The things being added are connected tail to tip. Now, what's the net result of that? It's a net magnetic field, and the field is a vector, so you could use an arrow to represent the net field. Which way does that net field arrow point? Well, the rule is always to start that net arrow at the tail of the first thing that was being summed and let the arrow go straight to the tip of the last thing that is being summed. There's the net field. That makes more sense, perhaps, if you think of these vector arrows as if they were displacements. If you go on some kind of movement that is really made up of two different movements, two different displacements, say this is your starting point, and then this arrow represents your first displacement. Here's where you start and here's where you end at the end of that first displacement. But this point is not only the end of the first displacement, it's the start of the second displacement. So the tail of the arrow that represents the second displacement goes here, right at the tip of the arrow that represented the first displacement, and that displacement takes you from here to here. So this is your final ending point, and then the net result is that you started the whole trip here and ended here. So the net displacement would just be a movement from there to there. And every other kind of vector addition works the same way, whether it's fields or velocities or forces or whatever. The net arrow starts at the very beginning or tail of the first thing to be summed and goes directly to the tip or the end of the last thing to be summed. Write that down in a place where you will see it, and that way you don't have to try to remember it. Like I said, it's one of those things that's easy to say and easy to think you understand, but it's hard to remember unless you let pencil and paper do the remembering for you. Write it down. Write those rules down. Stop the video, backtrack a little bit, and write those rules down. You'd be amazed at how much easier that makes things. Okay, let's look at another example. Say these same two currents, but now we'll look at a point over here on the left side. So current A, current B, and then point Y right over here. And same deal, the distance between current A and point Y is the same as the distance between current B and point Y. Currents A and B are equally strong, so the magnetic field here caused by A is just the same strength as the magnetic field here at Y caused by B. So what does the field caused by A look like? Draw the line that connects current A to the point that you're interested in. Then draw the line that's perpendicular to that. That's the tangent line to the circle that point Y is on. Tangent lines are always perpendicular to radii. That's why we drew these two lines perpendicular. And since this is the tangent line, then you know that the field must point one way or the other along that line. And the right-hand rule tells you which way. Thumb in direction of the current, which is pointing into the blackboard. When you curl your fingers into a circle, they flow clockwise. So the field lines that center on this current, right, the field lines that represent the field caused by this current, all circulate clockwise. So at this point, point Y, the field has to be pointing up to the left. And then what about the field at Y caused by point B? Same thing. Draw the line that connects the source to the point you're interested in. Draw the line that's perpendicular to that. The field caused by B must point along that line, because that line is really the straight line that's tangent to the circular field line that this point lies on. And the right-hand rule will tell us which way. Thumb in direction of the current, which is pointing out, pointing straight at us. Curl your fingers, and they curl counterclockwise. So the flow of the field lines that represent the field caused by this current all flow counterclockwise. So at this point, field is pointing down. The field is pointing down to the left. And then the net field at that point is just a sum of the field from A plus the field from B. Here's the field from A. Add to it the field from B, and to represent that addition, you put the tail of B0 at the tip of A0. These arrows should be of the same length because the fields are equally strong. That makes everything here nice and symmetric. And then the net field is represented by the arrow that takes you directly from the very start of the addition process, or the very start of this path, directly to the end of the addition process, or directly to the end of this path. So in other words, at both a point like this and then a point equally distant from the currents on the other side, in both those cases, the net magnetic field points straight to the left. All right, one other thing I should mention about drawing these pictures. So far, all the examples have been of currents perpendicular to the plane of the blackboard. How do you draw things when you have a current in the plane of the blackboard? Let's say a current that looks like that. Long straight wire, and the current flows this way. What do we know? We know that the field lines are concentric circles centered on this, which means, and those concentric circles are all in planes perpendicular to the current. So in this case, those circles in perpendicular planes will be circles in horizontal planes. And since they are centered on this, half of that circle will be out here in front of the blackboard, and then we imagine that the other half of the circle is behind the blackboard. So, and which way do those circles circulate? Right-hand rule again. Thumb in direction of the current, curl your fingers, and that shows you the flow of the field lines. And they'll be like this. So the field lines will actually be flowing this way. Which means they'll be coming out, which means the field will be pointing out of the blackboard over here and into the blackboard over here. The circle is in a horizontal plane. Half of the circle is in front of the blackboard, the other half is behind the blackboard. So in the plane of the blackboard over here, you've got the far left end of that circle. And when you're at the far left end of that circle, a straight tangent line, tangent to that circle at this point, will be pointing this way, exactly perpendicular to the plane of the blackboard. So on this side, at the far left end of any circular field line, the field must point either perpendicular out of the blackboard or perpendicular into the blackboard. And now, sorry about that. Maybe you noticed this before I did. I had this backwards. The field circulates like this, counterclockwise if we were looking at it from above, which means the field is, as I said, the field is pointing out on this side. I said it correctly, but I did not draw it correctly. And then pointing in on the other side. So when the currents are perpendicular to your paper and you have to draw them with these two symbols, then the field will always be in the plane of your paper. And vice versa, if the current is in the plane of your paper, the field lines point perpendicular to your paper. So because of all these weird directions, magnetism is more complicated than the electrical phenomena. So it takes a little bit of getting used to, and see how you do on your first crack at all these ideas in the assignment.